Today we are building a TBot. This is an XY Cartesian motion stage with a little twist, and we'll have some machining of unnecessary but pretty cool looking Isogrid parts, dealing with runout on very small tools, getting to know carbide micro drills, and full clench engaged thread milling, and maybe a blooper or two. Okay, cool. Let's get into it. So this is a big old slab of cast aluminum. It's half an inch thick by 24 inches long, and I want to say about 6 inches wide. This will form the base of the motion system, where the X carriage linear rails will mount, and the servos and the pulleys and kind of all the drive components. I'm using a 1/4 inch single flute carbide end mill, and I've used this in a couple other videos, and I'm really liking it just kind of as my go-to, get stuff done tool. I have a recipe that works pretty well at this point. It averages around 70 to 100 inches per minute at 24,000 RPM and 10% step over, give or take. And that does a pretty good job. I don't have to worry too much about it. You might see the less than ideal work holding in this setup. I really don't have an excuse. I was just being lazy. I need access to essentially the entire perimeter of this part. And so if I were to clamp it to the bed, I would need to use toe clamps and then switch toe clamps to get the other side in two different operations. Or use something like low profile clamps, but I don't have those and I would still have to be careful about not hitting them. So I just decided to go the lazy route, put it in the vise and throw some jacks on each of the sides, and it mostly worked. There's more chatter than there really should be. I'm now creating the floor and reference edge for one of the linear rails, and right about now I'm realizing I forgot to level the stock in the vise before I got started, which is obviously bad when you're trying to make a nice reference edge for a linear rail. So no problem, bust out the dial indicator and start indicating across the surface, adjusting the vise and the jacks to try to get everything essentially as parallel as possible. This is cast aluminum, so it's supposed to be pretty flat. Although this piece did have a 10 to 15 thou dip in the middle, and at first I thought this was distortion caused by the machinist jacks kind of pushing up on the edges, but I took everything out of the vise, set it on a flat surface, and confirmed that it does in fact just have a dip. So that was a little tricky to fix here since the jacks can only put upward pressure, and I would have to get some kind of toe clamp to pull down to kind of even it out. So I dialed it in as well as I could. I think I got it within a couple thou and called it a day. That was fine since I was going to be leveling off the important surfaces anyway. Then it was back to machining the mounting surfaces for the linear rail. One side has a reference edge that the rail butts up against, the other side just floats. And then a bunch of miscellaneous features around the parts, so different bolt holes and a few bores for bearings. And then we come to the operation I think I was dreading the most. This is a 2.5 millimeter carbide drill, and I have 20 or 30 holes I need to drill and then tap afterwards. I really didn't want to use carbide in this case. It's a small enough diameter that high-speed steel would be perfectly fine, and it would be a lot tougher and less likely to break. But it's metric. I don't have any metric collets. Drills, for whatever reason, don't come in standardized shank sizes for the most part, and so I didn't want to buy a one-off collet for a one-off 2.5 millimeter drill, and instead I grabbed this carbide drill, which does come in standardized shank sizes, so I could use my existing set of collets. And I promptly broke it. I had derated the feeds and speeds for this by like 75%, but clearly it was still too fast. Thinking about it, I thought, I should probably check the runout on these. If there's any kind of runout, that's going to be a sad day for me. Sure enough, there was about thou and a half of runout. And to be honest, I'm not really sure what counts as good or bad for a tool this size, but that seemed like a lot to me. So I tore everything apart, checked the runout on my spindle to verify it was okay, and then essentially looked through all my tool holders and all my collets to find the best set. They're mostly all cheap imports, so none of them are particularly good, but I found the best of them and did a thorough cleaning of inside the spindle and also the threads on the collet closer. And once I checked everything, I got it dialed into under half a thou, at least by this also admittedly pretty cheap indicator. Out of an abundance of caution, I also lowered the feeds and speeds and switched over to a pecking cycle. And then, what even is this? So I make a lot of mistakes and I show a lot of my mistakes on this channel. I think it's good for people to learn from, but I don't think this was my fault. I went back and I double checked the CAD, I checked my work offsets, I checked the tool height, everything looked good. I think Mach just totally dropped the ball on this one. As a software engineer, I know how hard it is to make good software, but honestly, Mach has been such a flaky, terrible piece of software, I am not at all surprised if it decided to just lose the tool offset and smash into the work. So I turned off the whole machine, turned everything back on, reprobed the edges, touched off the tool, and went about my day. And luckily, the rest of the drilling cycle went totally as expected. No more broken tools. I am happy I had the foresight to buy like 5 of these drills ahead of time, knowing I would break, well, probably at least a few. Next up is tapping all those holes. I don't have an encoder on my spindle, so I can't use a proper power tap cycle, but I can use thread milling. This is an M3 full profile or multi-point thread mill. This looked arguably even more terrifying than the drilling, but it actually went pretty smoothly. I didn't really have any incidents. The threads came out pretty nice. 5 stars, would recommend. The distance between major and minor on these M3 is only 0.5 millimeters, but I wasn't really sure how much meat a thread mill can take off at one time, so I opted to do 2 passes, each at 0.25 millimeters, just to be as safe as possible, because I only have one of these thread mills and I really didn't want to break it. They're not particularly cheap. I'll speed run through this next part. These are motor mounting brackets and relatively uninteresting. Bulk of the work was done with an 1/8 inch single flute end mill, and it was just a lot of adaptives and some slotting. I did take the slotting pretty slow because I have had troubles with them in the past, and again, was tired of breaking tools on this particular project. So it took a little longer than it probably needed to, but I also didn't break anything. Then we get to this final part, which I think might be in my top 5 most favorite machined items, at least so far. Spoiler, it came out pretty good. This is an intermediate linear rail carriage mounting platform. The carriages from both the X and the Y mount to both sides of this part. So it's essentially just a glorified piece of aluminum with some holes and countersinks in it. And it would have been, I don't know, 15 minutes tops machining time. But that didn't sound very fun. And I started thinking about it. I'm like, well, this part's going to be moving, not quickly, but it'll be moving. So maybe we could reduce some weight on it and, just practice machining that way. And I got the idea, well, hey, let's put an isogrid in this part. If you're not familiar, isogrids are basically a webbed structure made out of equilateral triangles kind of spread across the surface of your part. It's used in aerospace a lot for lightweighting things because it retains a lot of stiffness, but you can dramatically decrease the weight of the part you're working on. I'm not in aerospace, but I'm told isogrids are just very expensive in general because there's a ton of machining time to deal with all these little triangles. So you tend to really only see them in environments or situations where the cost of extra material far outweighs the cost of machining this expensive process. Payload prices on a Falcon 9, for example, are something in the range of $1,200 per pound. So for every pound of material you remove from your part, you are literally saving yourself thousands of dollars of rocket fuel. So it just makes sense to pay a little extra machine time. The roughing cycle with a 1/4 inch end mill took maybe 20 minutes, and so that wasn't too bad. But the rest of the roughing with this smaller 1/8 inch end mill took about 3 hours. And I didn't even bother doing any finishing passes because that was going to add another 3 hours on top of it. And honestly, it doesn't really matter for this part. But hey, this turned out really awesome. I think the part looks fantastic. Could use some deburring. I probably should have put a chamfer on everything because there's no way I'm deburring this by hand. But otherwise, it was basically flawless. I think it's a really cool technique. I'll probably isogrid more things just because, everyone needs a little isogrid in their life. So I lied. There's one more part, but I lost a lot of footage because my camera was overheating at the time. It's essentially the same operations as the X-axis, just for the Y. So there's a surface for the linear rail, a bunch of drill and trapped holes, various features. Not terribly interesting, so we can skip over this. All right, so what did we build here? This is a Cartesian system, so it moves in X and Y. It's a parallel mechanism, meaning that it has 2 motors that both drive both axes simultaneously. And it's kind of informally known as a TBot because it can make a T shape. So I'll dive into the individual pieces in a minute, but let's look at kind of an overview of how the system's set up.
We have two linear rails here for the X, and so the carriage can move back and forth this way. And then there's a linear rail underneath this to allow the Y direction going front and back. It's belt driven, obviously, as you can see here. So there's a single belt that starts up here, wraps around, goes around the first motor, wraps around the back where there's an idler, comes over to this side, wraps around the second motor, and then comes up to the front. So it's a single continuous belt that you tension at the front. And kind of the neat property of this parallel mechanism is you have to turn both motors at the same time to get coordinated motion. So in this case, if I take the motors and spin them opposite of each other, it goes in the Y direction. And if I spin opposite the other way, it goes positive or negative. And then if I spin them in the same direction, so they both go clockwise or counterclockwise, you get motion in the X back and forth. And so to get kind of coordinated motion of, say, like an interpolated circle, you drive both of these motors at varying rates to get kind of a different, oh, it's really hard to do by hand. Well, it's very counterintuitive to do by hand, but you get the idea where essentially the motion of X and Y is dependent on both motors at the same time. So why might you want a parallel mechanism like this? There's some advantages and there's some disadvantages. One nice property is that both of the driving motors are fixed. So these are bolted to the frame directly. They don't move with the carriage in X or in Y. You'll see with a lot of like 3D printers, one of the motors is mounted on, say, the X carriage, meaning that you've got two serial Cartesian mechanisms just stacked on top of each other. And you have to drive the mass of one of the motors with the other motor. And so you can kind of get imbalanced forces or just have to deal with kind of the mechanics of mounting a motor somewhere out here and dealing with tilt and tip and stuff like that. So that's one nice advantage. Another advantage is the fact that since they move together, you take the positioning error of each motor and they're averaged together because you have two different motors that are essentially working together to try to point the end effect or whatever you're working with at a specific location. And so when you combine them together in this manner where they both contribute to the motion, parallel mechanisms average out the error. Whereas when you have an X stacked on top of a Y, each one is in charge of its own error. So the X only contributes to the X error and the Y only contributes to Y, which sounds nice, but because they are stacked on top of each other, they're actually additive. So if the X is off a little bit and the Y is off a little bit, you end up with just the addition of those two errors, whereas a parallel mechanism averages them out. And then the third kind of like advantage of a parallel mechanism like this is that because you have both motors driving the carriages, if you have to move, say, in the X direction, both of their torque and force is going into moving in the X. And so you get combined forces where before you would only have a single motor driving in each axis. So that's cool. Why might you not want to use a parallel mechanism? Well, one, it's a lot more complicated. And so you've got arrangements like this where you have lots of belts going on, you have to deal with tensioning. The kinematics are more complicated because you have to deal with both motors moving all the time for every positioning. So it's not as simple as saying run your X, 100 millimeters. It's run your X and your Y X amount, it's a little more complicated. In this case, it's a pretty simple parallel mechanism and the kinematics are really easy to solve. But when you get into like 3 degrees of freedom or higher, stuff gets complicated really quickly. A big disadvantage of parallel mechanisms in general is that they have more limited workspaces than their serial counterparts. This arrangement is not the worst, but a lot of parallel mechanisms have considerably smaller work volumes. And so in this case, the Y can go out to about here and come back to about here. And so essentially you've got this much, let's move it out, you've got this much end effector space, which if we look at, in this case I've got about 13 inches from tip to tail, and the X direction is, I'd say about 14 or 15. So this is a 13 by 13 inch kind of work volume, and the whole thing is 25 inches wide. So, it's not the most efficient use of space, but it's not as bad as it could be. Okay, so now that we have kind of an overview of the system, let's start looking into the different details. So as I mentioned, there's 2 linear rails in the bottom and one underneath here. They're both 12 millimeter, 24-inch long, just cheap import linear rails. So they're not fantastic, but they're sufficient for this kind of prototype. This is a plate of cast aluminum, half an inch thick, and no particular reason it was cast aluminum. It was just the material I had on hand in the right size. There are 2 shafts that go through to the motors, and as you can see, the motor is actually a little further away. So underneath there's a pulley arrangement to gear down the motors and give better resolution. The pulley belt system, this is just GT2. I believe this is steel reinforced GT2 because it's what I had on hand. It's tensioned at the front. If I bring it back, there we go, this way. So it's tensioned at the front here. This is just a 3D print because I wasn't quite sure what I wanted in metal yet, so I just fabbed this out of PLA real quick. There's 2 M3 bolts on each side that has a little moving carriage that pulls in and out and captures the belt. This needs to get replaced. It's not really sturdy enough to tension this stiffer belt, and I just don't like the arrangement, but it works enough to kind of demo it. In the middle here, we have 4 608 bearings that are inside of 3D printed idlers. And again, these I'll probably replace with metal, but this was sufficient for just testing it out. The plate underneath is, I think it's just 6061, something I had on hand, with this really cool Isogrid. Totally unnecessary. I just thought it'd be fun to machine some Isogrid. It's not at all required. Technically, it's a little lighter weight, so the moving carriage has less mass to throw around. It doesn't matter. These servos are much beefier than the weight of, I don't know, 500 extra grams. There is a set of machined holes on the underside here, and this was important to mount the 2 carriages that are on the underside of the y-axis. Essentially, the way this is arranged, because it's using the same piece that's mounted both for the X and the Y, you need access to at least one of the sides to mount the other set of carriages. So in this case, this was assembled first with these sets of rails and then the moving plate, and then I came through with a screwdriver and installed the carriages on the underside. So this plate that goes across the top, it serves 2 purposes. One, obviously, is it's the mounting point for the linear rail to give you the Y motion, but you can also see these tapped holes along the side. So these are 1/4-20 tapped holes, and the idea here is to provide mounting locations for different end effectors. And so I have some plans in mind to use this kind of Cartesian setup for, and I was trying to think of a way to do double duty on the axis as well as mounting things that I want to hang down. Not quite sold on this setup. I feel like it's going to get in the way with this belt, which I perhaps didn't really think through very well. But at least to start, the idea is that I'll be able to, I don't know if I use this popsicle stick, mount something in one of these 1/4-20 holes or multiple somethings and have it hang down into the work volume underneath. The motors themselves are NEMA 17 package, but these are actually servo motors and not steppers. Forget the company. I can link it in the description. I think it's Anaheim something. I found them on eBay for super cheap. The reason I grabbed these servos in particular, one, I want to drive these with an ODrive and get that sweet servo action as opposed to steppers. So that was the first consideration, and I could have used just like a hobby brushless, but this was in the right size and shape, and it has the NEMA mounting package, which was nice. But the really critical part, which is why I grabbed these off eBay, is that they are double shafted. So there's a shaft here on the top, and then there's also a shaft that goes out the bottom. So why might you want a dual shaft motor like this? So the most compelling reason is to have the load driven on one side. So down here I've got a stepper belt, which is driving the whole system. And then on the top, you can mount an encoder to close the loop and actually know precisely where the motor is at all different times. There's two M2.5 mounting holes here. I'll fabricate a little bracket, and I've got some optical encoders that can go on here. They're, I think, 16,000 pulses per revolution, so you can get pretty fine control. In addition to it being 16,000 pulses per rev, it's also geared down, I want to say 5:1 on the underside, and so that, multiplies out how much encoder resolution you get per millimeter of travel. Here's a look at the underside. Pretty unexciting. This is a 3D printed pulley just because I was silly and bought the wrong size shaft. So this is a temporary print just to couple everything up. And then I believe this was a 20 tooth and this is a 60 tooth. Again, the idea here is just to give us a little more gearing down to help with load. This is going to be a slow machine, so it doesn't really need speed. And more importantly than going slow is that it gives me more encoder resolution, because for each turn of this, which gets me 16,000 pulses, you move a much smaller amount because it's geared down. Here's a close-up shot of the kind of interior of the carriage system. So you can see down here, the linear rails are attached on the underside, and then the other set of linear rails are attached to this top plate, the pulleys, and then the little Isogrid system. Generally, this project went pretty well so far, but there are a few glaring issues that I didn't quite anticipate. So you'll notice on this linear rail, there's a nice, set of bolts as you would expect, holding everything down. But if you go to the other end of the rail, I don't know how well this shows up on video, there is a distressing lack of bolts towards this end, except for the very end where I've managed to put one in. This was entirely my fault. I found something I'm worse at than machining, and it's apparently CAD work. So I, for whatever reason, had my measurements wrong of the hole spacing, or the file I used online of this linear rail was not accurate, or charitably maybe these aren't up to spec because it's a cheap import rail, but I'm pretty sure this is just my fault. Whatever the reason, the hole spacing was off by, I don't know, maybe 0.5 millimeter per hole. So as you work your way in one direction or the other, the holes stop lining up sufficiently. You could get away with it on one side because it's aluminum and you can kind of force your way in. At some point that just becomes not possible. And so you have this situation. Luckily, well, for better or worse, by the time you get to the end, there's a sufficiently large gap where the hole no longer intersects the hole at all. And so I managed to drill and tap one at the very end just to keep the rail down. So this is clearly not what you're supposed to do with somewhat precision linear rails. If I were to do this again, or for something that mattered, this would basically have been a scrapped part and start over. In this case, I didn't care too much. I kind of smushed it into place, and there is more drag on the rails than there should be, and it probably will decrease the lifetime of the bearings because of it. Things aren't quite parallel. It's okay for this case because it's just a prototype, and I have enough adjustment elsewhere in the system that I can kind of make up for it. But yeah, this was a pretty silly mistake. Kind of amusingly, since I had such a silly mistake with the spacing, I did try to do the right thing with these linear rails. So you'll notice that on this side, the rail is positioned right up against this machined edge, kind of supposed to be used as a reference edge. And so the idea is you first mount this one, confirm that it's straight with a precision straight edge, and then once this is in place, you mount the second rail, which doesn't have an edge close to it, and this is basically floating. And the idea is you mount the actual carriage that you want to be running on this, you mount it and tighten them down sequentially so that it kind of floats itself into parallelism. That was the plan. It all went out the window when I messed up these mounting holes though, because nothing is where it's supposed to be. Each rail is kind of twisted and warped in its own unique way, trying to fit into the improper mounting holes. So that was kind of silly, but I did really try originally to do this correctly. But lessons learned. One of the other not so fatal flaws, but irritations, and luckily this one's fixable, has to do with the Y carriage and a little bit of asymmetry that I designed into it. So the linear rail is mounted on the underside against, again, kind of a reference edge like I did down here. But I did it in a manner that makes it a little asymmetric. And so the rail is actually over on that side, and there's extra space on this side. So what that means is that kind of the center of the rail is offset from the center of the pulley travel. And in practice, what that ends up doing is there's space on this side for the belt, but there's not space on this side. The belt is actually touching and rubbing right here. It's not drastic, so things can still move freely, but it is irritating, and it'll add wear to the belt, and it adds a lot of friction to the system. So that was kind of just a goof on my part for not fully modeling this out and expecting that to happen. Luckily, there is plenty of extra meat on this side, so I can just mill this piece down by, I don't know, 1/4 of an inch, 1/8 of an inch, and this will no longer rub. So that's a fixable problem. All right, well, I think that's all I've got for you today. I'm going to do a little extra machining to fix some of the issues that I talked about. And then the next step is to start wiring it up. So wire up the servos and fabricate the mounts with encoders, get the ODrive running, and then start programming it. And then we'll see what it can do. If you're interested in what this machine is for, I don't want to spoil it yet. I think it's a pretty neat project, but it's not quite ready, so you'll just have to tune in later for the next video. Thanks for watching.